recording. Perfect. And yeah, Professor Cohen, you're good to go.
Okay, cool. So it's my great pleasure to introduce Vicky Meadows. So I've known Vicky since I was a wee graduate student at the University of Washington, where she was a professor. But before then, so going back to her beginnings, Vicky got a bachelor's in physics from the University of New South Wales in Australia, followed by a PhD in physics and astrophysics from the University of Sydney, and then spent a good chunk of her the next stage of her career at the Jet Propulsion Lab in California, before moving up to the University of Washington, where I met her. She came there as a professor, and basically was granted tenure pretty much instantly, because she was already a hotshot, being the PI of one of these huge NASA Astrobiology Institute nodes, the Virtual Planet Laboratory. And so that Virtual Planet Laboratory still exists to this day. I have heard, on rare occasions when Vicky is willing to brag, that she is like the longest standing PI of one of these NASA Astrobiology Institute nodes, and so has been doing it for something like 20 years. And along the way, Vicky has won many awards, including the Frank Drake Award for research accomplishments in astrobiology. She is an associate editor of Astrobiology, the Astrobiology Journal. She was part of the US Decadal Survey that must be just about wrapping up. I hope it's wrapped up at this point. Anyhow, she's an expert in exoplanet habitability, but also solar system planets, and in fact started her research career studying Venus and the solar system planets. And so I think today we're going to get kind of a throwback to some old school Meadows science in the context of the purported biosignature recently announced on Venus. So without further ado, Vicky Meadows, take it away.
Okay. So let's see. Hopefully everybody can see that.
Yeah, it looks great.
Okay, and you can hear me too, by the sounds of it. All right, so great. So lovely to be here. Thank you for that lovely introduction, Nick. Yes, I've been around for a long time. So, and yeah, I've been dragged kicking and screaming back into Venus. It's always been my love, and I've kept it sort of going on a low simmer with students working on it. Most recently, Jared Arney has kind of been carrying the torch for Venus for me for quite some time. But yeah, but with this recent development last September, I sort of went back in with both boots on. So I'll talk a little bit about basically a pair of papers that we have got accepted that should be out in APJ letters pretty soon. But what I'm going to do really in this talk is lay out the case for why people thought there was phosphine on Venus, and then I'll lay out an alternative hypothesis that it might just be sulfur dioxide. So that's what I'm going to talk about today in this presentation. Okay, so I don't actually know the backgrounds of all of the audience members here, but so I'm just going to do a little sort of mini crash course on little facts about Venus that you probably need to know to be able to understand this story. But I don't really have time to go into all of Venus, although Venus is extremely fascinating because it is in many ways the planet both most and least like the Earth, and that is because of its divergent evolution. It started out with a similar size, mass, and density. It was formed in the inner solar system. So it has these sort of basic characteristics that make it look quite Earth-like when compared to the Earth. However, it has this crushing 93 bar carbon dioxide dominated atmosphere, 475 Kelvin of greenhouse warming from that, which gives it about a 730 Kelvin surface temperature. It has a massively desiccated atmosphere. It's about 20 parts per million of water on average throughout the atmosphere. And it has this dense bank of planet-wide sulfuric acid clouds, which obscure the surface to a lot of wavelengths, but not all of them, including some radio and near infrared. And my PhD thesis, where I started, was actually looking through the near infrared spectral windows on Venus to study the surface of the planet and the lower atmosphere, and to look for water vapor in the lower atmosphere. And I kind of joked that, I started I also looked at air glow in the upper atmosphere of Venus, which was produced by oxygen, looking at how that actually traced mesospheric dynamics in the upper atmosphere. So I always make the joke that, I started out my career trying to look for oxygen and water on Venus, which is arguably the least habitable planet in the solar system. So again, that composition, Venus is predominantly carbon dioxide, 96 point something percent, with nitrogen pretty much filling the rest of it. And then there are a bunch of trace gases, of which sulfur dioxide is the dominant trace gas at 150 parts per million on average throughout the atmospheric column. And then we have a bunch of other things, the water vapor, carbon monoxide, helium, neon, argon, that sort of thing. But mostly you're talking about a CO2 dominated planet. All right, Venus atmospheric regions. I'm going to be throwing around some of these terms, and so it's important to kind of know what we're talking about here. I'll actually start at the surface and work up. So the surface at the bottom here, 730 Kelvin, a basalt layer, volcanically emplaced. The lower atmosphere below the cloud deck goes from the surface up to about 48 kilometers. And then you have the clouds from about 48 kilometers up to 68. So throughout this talk, if you remember 48 to 68 as the cloud region, then that will help in disentangling some of the information in here. The cloud top is at about 68 kilometers. It varies depending on, how thick the H2SO4 is that day, but somewhere between about 64 and 70 kilometers is typically where the cloud top altitude is. And then above that, all the way up to the exosphere, you basically have this region that's called the mesosphere. And so that's the region above the clouds. So it goes from 68 kilometers up. There's actually haze, the sulfuric acid haze that goes all the way up to 90 kilometers. So that mesosphere is not completely empty, but the predominant cloud deck is from 48 to 68 kilometers. Okay, because that vertical distribution is going to end up being kind of important. All right, so this paper, landed like a huge bombshell in both the Venus and astrobiology communities back in September. So it was called Phosphine gas in the cloud decks of Venus, and led by an observing team led by Jane Greaves. What it predominantly was an observing focus proposal that had used the JCMT and AMA telescopes to observe a particular line in the millimeter wave regime that could potentially have been due to phosphine. And then the rest of the paper, and of course it was a Nature paper, so they didn't have a lot of room, was spent, talking about what could have produced the phosphine and coming to the initial conclusion that they couldn't think of anything non-organic or abiotic that could have produced it. So maybe potentially it was due to life. And so again, they say by analogy with biological production of phosphine on Earth, the fact that phosphine is on Venus could indicate that there's life in the Venus clouds. So of course, that sparked a whole bunch of media coverage. Yes, really could be life in the cloud tops of Venus. Astronomers see signals in the clouds, so there could be life. Astronomers obsessed with a particular gas, don't mention the gas. And then signs of life, even as recently as this last month, Sunday, 24th of January, signs of life found in Venus clouds rekindle ideas of floating cities for humanity. So it certainly, captured everybody's imagination as being something, really, really very exciting. So what I'm going to do now is go through sort of the original paper and the argument that was made for why what they had detected was in fact due to phosphine. So there were two telescopes that we used to make the detections. There was the James Clerk Maxwell Telescope on Mauna Kea and the AMA Observatory in the Atacama Desert. These are millimeter wave radio telescopes. AMA is a radio interferometer, and JCMT is a single dish. Because JCMT is a single dish, it will measure the total flux emitted by sources in the direction of the antenna pointing, independent of spatial scale. So basically, if it's on Venus and visible at the wavelength you're observing at, JCMT will pick it up. AMA, however, is a radio interferometer. And so the maximum recoverable spatial scale and spatial resolution are determined by the space between correlated antenna pairs. So the radio interferometer can be reconfigured so that it uses a bunch of different baselines to try and image the thing that it's looking at. And one of the main points here is that in the Greaves et al. Paper, and I'll go into this in a little bit, they needed to keep the noise levels down, they needed to exclude baselines that were shorter than 33 meters from the Atacama array. But these shorter baselines are required to measure flux over large spatial scales. So if you want to try and be sensitive to something that may be evenly distributed across the disk of Venus, then you're not going to be as sensitive to those broadly distributed things if you cut out the shorter baselines. So that's the sort of the main takeaway from that. So we're going to go through these two data sets, and we're going to see some things in one and not in the other, and I'll try and explain based on this sort of observing setup why that is happening. So in the initial discovery paper, when I first read this paper, I thought, wow, this sounds pretty convincing. They have observed, the same line in basically 3 different modes on 2 different telescopes, and they keep getting, this result. So the first result they got back in 2017 was with the JCMT. And can people see my cursor? Is that something you can see?
Yes. Yeah,
yes,
we can see your
right.
cursor.
All right, so here's the JCMT line that was observed at 266.94 gigahertz. And this is a region where phosphine potentially absorbs. And so they were able to see this line in the data, and they were able to fit it with about 20 parts per billion of phosphine. In fact, the apocryphal, the story goes that they were actually looking at this line to show that Venus didn't have it. And then they saw something there. Okay, so they were like pretty excited about that. So they went and got observations to follow it up in 2019 with ARMA, which is a more sensitive telescope. And then they observed this feature in the narrowband at something like 15 sigma, which is a pretty solid detection. And then they also went into the wideband, which is this dashed line here, and they saw something similar at about the same rest frame velocity, although not really close. And I asked experts and said, is this like, typical to have things shifted like that? And they said, no, not really. So that was already maybe a little bit concerning that those things didn't line up in the narrowband and the wideband. Nonetheless, some pretty convincing looking detections of this line that could potentially be phosphine. I will point out, though, because of the removal of the baselines and the loss of sensitivity to things on different spatial scales, they couldn't use the ARMA narrowband data to do the abundance determination because of something called line dilution, which is the fact that they're not observing things on all spatial scales. They're not observing the whole Venus. And so as a result, they only observe a fraction of what's there, and that's called line dilution. So they estimated their line dilution was about 80%. Meaning that whatever they saw here really needs to be multiplied by about 5 to match whatever was being seen with the JCMT whole disk. All right, so the other thing they had to do in the data analysis was get rid of these very strong, what are called spectral ripples in the data. And so this is where some people think that there may have been an issue in the actual fitting and analysis of the data. Because you can see here in this blue line in particular, the way you fit the continuum really affects the strength of what you infer the absorption line to be. Why are there spectral ripples in the data? I'm not a radio observer. I'll say that right up front. I'm a Venus expert, but I'm not a radio observer. But they tell me that when you have a very bright extended source like that, especially if it's overfilling the beam of the telescope, that you can end up with all sorts of additional reflections within the instrument. On geo surfaces, the receiver cabin, everything. So this sort of thing is happening within the instrument simply because most telescopes are not designed to look at Venus. And another one of my favorite sayings is, one does not simply walk into Venus observing. Venus observing will challenge any telescope at any wavelength. It is like, the third brightest object in the sky, and most telescopes really are not designed to deal with that. They're designed to look for extremely faint objects. So you already have to do a whole bunch of, preliminary work and trying to make sure that you get the data with the least noise and the least scattered light and the least scattered whatever all together. So in an attempt to reduce the magnitude of those ripples, they cut out the shorter baselines, which meant they became less sensitive to things across the disk. But one of their spectral ripples actually had a similar width and depth to the spectral detection, which concerned a few people early on. But because they had to cut out the baselines, they just became less sensitive overall. So this is a map of what they're seeing on the disk. It actually shows they are more sensitive to things on the limb of the planet. And they used a weighting function to estimate the sort of the lowest altitude of which emission was coming to backlight whatever absorption was being seen above that, because they're seeing essentially an absorption line. That's what that feature was that they were seeing. So they estimated that the emitting layer within the planet at that wavelength, so the layer hot enough to emit and then cooler gas above absorbs, was at 56 kilometers. So remember, 48 to 68, 48 to 68. So 56 is right in the middle of the cloud deck, right? And so they said, well, theoretically, basically anything above that could absorb. This is the emitting layer. Anything above it could absorb because we're cooling with altitude. So they inferred that the phosphine could be coming anywhere from above that, which allowed them to potentially place phosphine within the clouds. Okay, so that seems like a simplistic story. You've got a strong line where phosphine absorbs, seems to be coming from inside the clouds based on your arguments. But here's sort of the really interesting point. The 266.94 gigahertz is this line here. And that line, not only does phosphine absorb there, but so does sulfur dioxide. And so sulfur dioxide, remember, is the most common trace gas in the atmosphere. It's the third most abundant gas in the Venus atmosphere. So they knew that, and they knew that they would have to disentangle the phosphine from the sulfur dioxide. So what they did was they didn't do an SO2 phosphine challenge. They didn't try and calibrate for the SO2 being there in the first observation where they didn't expect to see anything, right? So they didn't actually check it at other SO2 lines. So in the ARMA data 2 years later, they said, okay, let's go look for SO2 as well and figure out how much SO2 is there compared to the phosphine. And that will let us know whether we can claim that there's any phosphine in this line. So they went to observe at 267.54, which is a clean sulfur dioxide line. So actually, if we go back here, where are we? It's one of these lines over here. So there's a very strong SO2 line, a little bit longward in frequency space in the spectrum. So they went to go and observe that. And what they saw was this bolded bit here, which was absolutely nothing. They saw absolutely no detection of SO2 in their spectrum. So they said, well, okay, let's be generous. Given all these wiggles that are going up and down, let's say that, the maximum non-detection is now, round about here, given how high the wiggles could possibly be. And so they fit that and they said, well, that's equivalent to about 10 parts per billion of SO2. If we assume that there's 10 parts per billion of SO2 at this combined frequency of phosphine plus SO2, the SO2 would be the green bit, and the data is the red bit. So they're saying, okay, fine. So this would be how much SO2 there would be based on the limit we get from this calibration line. So therefore, the majority of this line must be due to phosphine. And they then also assumed that the majority of the line seen in the JCMT data was also mostly due to phosphine. Okay, so they've done due diligence, they've done an experiment, they said, okay, I'm trying to figure out what my contamination level is. Contamination level looks low, therefore I'm potentially looking at phosphine. So that's where I kind of came into this. And at the point I was reading the paper and I was like, okay, well, this all sounds really convincing and I'm pretty excited. And then I was like, hang on a minute, did you say 10 parts per billion of phosphine and you think it's coming from the clouds? And at that point, that was kind of a piece of cognitive dissonance for me, because I knew that the SO2 within the clouds was likely much higher than that. And in fact, in their own paper, in their original paper, they actually run a typical Venus SO2 profile through here, which has Venus at 10 parts per million, not 10 parts per billion in the cloud deck. So at that point, my interest was piqued and I was like, well, that's really interesting. Why are they seeing such a tiny amount of SO2? And of course, a tiny amount of SO2 favors the phosphine hypothesis, but was jarring with my knowledge of what Venus actually looked like. And there's also, more in-depth studies of phosphine, of SO2 above the clouds in this paper by Belyaev et al. In 2012 and in 2017, where they actually use the Venus Express with two different types of instruments in occultation. And they were able to map out essentially, actually, this one is direct imaging, I think. This one is the infrared instrument and then the UV instrument and occultation above. And so we do have a fairly good idea of how much SO2 there actually is above the clouds. And even that also would predict, even 1 part per million or 10 parts per million. So significantly more than 10 parts per billion in the clouds. Another interesting thing to know is that phosphine, and this is again from their own paper, from the Greaves et al. Paper, but it's also emphasized in the Baines et al. Paper. Phosphine itself would be very, very chemically fragile above the clouds. So they calculate that it would have basically a sub-second lifetime in the Venus mesosphere. And so they're anticipating a very rapid drop-off in abundance with altitude. So if we look at this mixing ratio graph over here, they're positing that there's a source of phosphine in the clouds at this position. That will then be thermally decomposed as you go down deeper in the atmosphere, and then chemically and photolytically destroyed as you come above the clouds, right? So remember, cloud tops are about 68. So we're starting to see a drop off in phosphine abundance as you head up into the clouds. So now there's a paradox. So if the observations are really probing the upper cloud, then the SO2 abundance should be significantly higher, in which case do you still need phosphine to explain the line absorption? If the inferred low abundance of SO2 is real, though, then that suggests that the layer being probed is in fact above the clouds, where it's really difficult for 10 parts per billion of phosphine to survive or be due to life. And so at that point, I'm like, maybe we should look at this in more detail, because I can't reconcile the abundance that they're claiming for the SO2. So that led us to write this paper, which was led by my then postdoc, Andrew Lankowski, and me, basically working as a pair, but ably supported by this other team. And in fact, our other real MVP in this, apart from Dave, who's always fantastic at all sorts of radiative transfer, was Alex Aikens, who was someone who we brought in because we are not experts on millimeter wave observations of Venus. And so Alex, in fact, he is Paul Steffes' student. For those of you in the Venus community, Paul Steffes is legendary for doing radio observations of Venus. And in fact, for detecting phosphine on the giant planets. So when I first heard of this, I called Paul up and said, hey, Paul, I've just found a project that combines your two main interests. And he put me onto Alex to bring into the team. So in this paper, we explored whether the absorption detection was in fact due to phosphine and whether in fact it was coming from the clouds. And so to do that, what we did was a whole series of experiments running different, what I call universes of Venus, different types of Venus. These things are what we call spaghetti plots. I don't know if people are used to looking at them, but this is essentially the vertical distribution of a constituent in the atmosphere, as a function of altitude on this side and pressure on this side. Over here, we have the Greaves et al. Universe, where we put in the abundances that they inferred. When they fit their 20 parts per billion of phosphine from the JCMT data, they assumed it was evenly mixed all the way through the column, which is in fact, and that's that purple line here. But that actually contradicts their photochemical model of where the phosphine would actually be. So that was actually a contradiction within the main paper as well. But we also model their tiny amounts of SO2, and we look at also the distribution down through the clouds. They assumed it was kind of evenly mixed, and we say, well, let's assume it increases with altitude to match the 130 parts per million that we see in the lower atmosphere. So we'll do that bit. We put in their water vapor abundance, which doesn't end up being that important. Over here, we ran our universe where we tried to do a really great fit to the data using what was known about sulfur dioxide and the profile that we know for sulfur dioxide. So you can see this Belyaev fit here, which I'm just running through, and the sort of all the data, the existing data for SO2 on Venus that runs through. And then we also just specified in the paper our cloud distribution, what we were modeling. So the first experiment we ran was just to see if we could recreate the Greaves et al. Results, because again, we actually weren't expert in modeling at millimeter waves. So we wanted to make sure our radiative transfer model was up to that. So we modeled their universe with the SO2 and the phosphine at the abundances that they expected. And we got a reasonable fit to the JCMT data doing that. And that was assuming the SO2 is evenly mixed at 10 parts per billion down through the cloud deck. Then to test sensitivity to being in the clouds, we ran instead this SO2 profile that increased rapidly with decreasing altitude, right? We said, okay, let's do a more realistic SO2 profile. And we seem to have a tiny bit of sensitivity maybe to what's going on in the clouds, but certainly not a major sensitivity to what is in the clouds. And so that was kind of showing us that, if you change the profile of something like SO2, for example, you don't get a really big change, which implies that they're not really sensitive to what's going on in the clouds. Then we ran, again, their universe, but their photochemical universe with the phosphine, and that's the blue line here, the phosphine, being produced in the clouds, potentially by their putative biosphere, dropping off below and dropping off rapidly above. And we said, okay, if it really does have that distribution, what would it look like in the spectrum? And here's the actual detection line, and here it is matching with the JCMT data. So we showed, as a test, that the phosphine distribution didn't appear to match the data that they claimed was the phosphine detection. But again, a second point that says, you know what, you don't seem to be sensitive to whatever's in the clouds. When we put stuff in the clouds, you don't see it. You don't see an increase in the SO2, and you don't see the phosphine actually showing up in the line. And I just want to point out that actually the way this went, we went we're going to do a refereed publication route. So we weren't part of the initial sort of backwards and forwards discussion that was going on. So we actually submitted this before the Villanueva paper was brought out, but they also pointed out that this photochemical profile didn't seem to match the data as well. So I'll absolutely give them credit for that. So that's two of us that came to that conclusion. So then we said, okay, we don't seem to be sensitive to stuff in the clouds. Where are we sensitive? Where is this line actually coming from? And so we modeled it both for phosphine, which is over here on the right, and we modeled it for SO2. Now this plot here is something called a Radiance Jacobian plot. And what it is our radiative transfer model, which calculates the interaction between, incoming radiation or thermal radiation and the gases in the atmosphere. We're able to use that to perturb the abundance of a given gas at a different level in the atmosphere and then see how that changes the observed absorption line. So I can go in and I can go, okay, let's do 10 times the amount at the cloud top and see what happens to this line. Let's do 10 times, 2 kilometers above the cloud top, see what happens to this line. And so we're able to map the sensitivity of things at altitude to changing this line. And what we see in the SO2 is you definitely see this emitting layer, as they assumed, from the sulfur at about 57, the sulfur dioxide from 57 kilometers up. But the absorption line itself, what we are seeing, all the way up to the continuum basically, is initiated at about 80 kilometers up, which is, at least 10 to 12, potentially 15 kilometers above the cloud deck. Okay, so this absorption line is coming from above the cloud deck if it's SO2. If it's phosphine, similar story, coming from starting at 75 kilometers up, but still a bunch of it still absorbing at about 100 kilometers up. Okay. So this is important because what it's showing is that the thing that they observed, that spiky absorption line, is in fact generated in the mesosphere above the clouds, whether it's phosphine or SO2. So what they're seeing is not in the cloud deck. And then you get to the point where, okay, if this is phosphine, and it's 20 parts per billion at these altitudes, as they believe it potentially is, based on their fit, then the flux of phosphine must exceed something like 100 times the Earth's photosynthetic oxygen output to maintain that much phosphine above the clouds. Okay, so chemically that doesn't make a lot of sense. So we've got two things going here. We've got, okay, it doesn't seem to be above the clouds. If it is above the clouds, there has to be this amazing biosphere. If it's a biosphere that's producing it, that's like 100 times more productive than the Earth's photosynthetic biosphere, which would be a hard sell. But then again, maybe it's just SO2. So let's explore the SO2 line then, and have we gotten that right? And I will point out here too that, by the way, even though we show that the absorption line is coming from above the clouds, that doesn't rule out sulfur dioxide. It doesn't rule out phosphine being in the clouds, because the phosphine in the clouds will be producing the continuum essentially, if that was what was happening. But the point is, because of the noise in their data, they can't see what's happening in those wings. So they really don't have any sensitivity to what's happening within the clouds. All right, so how do we choose the best sulfur dioxide value? That was tricky for us. And the thing is that sulfur dioxide in the upper atmosphere changes dramatically. It changes on hourly, daily, and yearly timescales. We've seen what seems to be injections of it from the lower atmosphere that some people thought were huge volcanic eruptions. And then you can have a long sort of decay of it. So there's also these large sort of secular variations. I will say though that the SO2 in the upper atmosphere, the volcano theory is matched by another one that simply says, hey, there's 130 parts per million of SO2 in that lower atmosphere. If you burp even a little bit of that above the clouds, it's going to produce a huge abundance variation at that time. So SO2 changes on hourly, daily, and yearly timescales, potentially depending on how much it communicates with the huge reservoir of it below the clouds. And so these are measurements again from Venus Express showing the different abundances that you get actually at different points on the disk. These stellar occultations are showing what's on the night side of the planet. And at the time that Greaves et al. Observed, they were kind of half and half with day side and night side on the planet. So the night side values do potentially matter. And different values were obtained near the terminator, and on the night side. So you kind of have to sort of smush those together. So what we went and did is looked for cloud top SO2 values that were around about the time that they took their JCMT data. So they took the JCMT data in June of 2017, and we found cloud top SO2 values from July of 2017. So these were taken with the TEPS instrument, doing this in the mid-infrared from the ground, monitoring cloud top SO2. So we took that value where the SO2 at 65 kilometers at the cloud top, which again, we may not be sensitive to, but it helps us pin our profile. That was in the range of 200 to 300 parts per billion already. So not even close to 10 parts per billion at that point. And then we looked at these profiles of the existing SO2. So, 200 to 300 parts per billion would kind of be down in this range here, which is sort of, consistent with the data that was coming out from the VEX, the Venus Express observing as well. So we used a profile like this, pretty much pinned to what we had actually been able to see from the ground. So that is the profile we used. And this is sort of the slew of different SO2 measurements that are known. So we picked something that was kind of calibrated to sort of the SO2 abundance at the time of the observations, or within a month of the observations, but also following a well-known profile for that SO2. So here's our fit to the JCMT data. So the orange is the JCMT data. The black line is our fit using that profile. You can see it fits really well on depth and width of the line. And these gray lines here are kind of the plus or minus 1 sigma models for the JCMT data. So, I mean, a criticism that can be said is that, well, nobody's really observed this high in abundance of SO2 in the upper atmosphere with millimeter wave observations, although those are limited to a time when there was a secular low point in the SO2. But nonetheless, I want to say that, given the 1 sigma errors on this, we have a pretty wide range of potential values that the SO2 could be. Okay, so we fit the JCMT data. So let's go back now to the SO2 reference lines over here. They are now about 10 times larger than that 10 part per billion SO2 limit that Greaves et al. Set as the reference that said you can't have any more SO2 than this, right? Otherwise the data would preclude in the clean line. Okay, so now we have a paradox, which is like, okay, I can fit it with typical SO2, but if I do that, we should have seen a stronger SO2 reference line. We should have been able to see that in the data, and yet it was not seen. So what is going on? Why can't we see the SO2? So that's where Alex comes in, because Alex, being an expert observer, said, oh, hang on a minute, they removed the 33-meter baselines, and if SO2 is uniformly distributed across the disk, then they're going to end up with a pretty aggressive line dilution from that. And so he has a model of Venus as observed by AMA, which he can use to determine what the actual line dilution would be. So the amount of radiation, coming from the planet that you would lose on various spatial scales because of this line dilution. So he calculated that you'd actually end up with maybe a 95 to 97% line dilution because you remove the 33-meter baselines, which would suppress the SO2 by a factor of 20 to 33 times. Okay, so if we now go back and model our nominal Venus SO2 profile suppressed by that amount, we're back underneath the limit for the 10 part per billion limit. So what we're saying is that the SO2 very well could have been there in the AMA data at typical abundances, or maybe less or maybe more because it's highly time variable, but it could have been there at roughly in the ballpark typical abundances, but not being seen because of the way they set up the observing array. Okay, so that's where we were. So now we actually had a complete story about how things were where things were seen, that they could be fit by SO2. The fact that things were not seen was explained by the line dilution, but there was one glaring problem, which that our hypothesis would predict that if the 266.94 line was also due to SO2 only and no phosphine, then it should also not be there. It should also be very heavily suppressed. And yet they claimed in their data in the initial paper that they had this fantastic 15 sigma line detection there, right? Okay, so we come up with our theory and we think, look, we think it's probably much more likely to be SO2, but this anomaly is very difficult to explain. However, while all of this was going on, the rest of the community was also putting out sort of initial discoveries. And what was happening was that people were questioning the significance of the ARMA detection lines. Okay, so this is a paper put out by Ignace Snellen et al. Very early on. And he reanalyzed the original ARMA data and showed that, using that 12th order polynomial, you could potentially fit the data to give 15 sigma features at multiple positions that weren't, the putative phosphine line. And so when he used, a less parameter-freed polynomial, he was not actually able to recreate a significant detection. So when he uses, a lower order polynomial, he gets, a line that looks like this at the position, but then we also have lines that look like this on either side. So it didn't seem to be particularly significant if you didn't use that higher order polynomial. Similarly, Villanueva, working on the original ARMA data set, also did the same thing. They essentially refit, and they also showed the danger of, depending on your polynomial fit, you could really change the significance of the detection of the line, whether you allowed it to fit at the line position or not. So they also said that they claimed that they didn't really see anything in the ARMA data at that position. And they also argued, again, that the 266.94 could probably be fit by SO2. They used 100 parts per billion evenly mixed with the mesosphere. They didn't, match the data at the time of observation or whatever, but they used 100 parts per billion and said, look, this roughly matches. And they also used a simplistic line width argument. They didn't do the Jacobians, but they did a line width argument and said, look, this line core must be way above the clouds, in which case, again, you probably need to explain how your phosphine managed to survive up that high. So this is not a straight, this story doesn't go in a straight line. So then the twist was, while we were all working on this, the ARMA data was basically brought back under embargo because there was something wrong with the actual analysis script when the data were handed to Greaves et al. So the data was being reanalyzed by the ARMA team, who felt that something had gone wrong in the way that they had actually done the data. So when the reanalyzed data came back, reprocessed data came back, the phosphine line was no longer at 15 sigma. They're claiming it's still here in the data using their 12th order polynomial fit. But it's now only at a significance of about 4.3 sigma. And now it's equivalent to 1 part per billion of phosphine in this data. But I will note that they're not taking into account line suppression here, so it could be higher than that. This is the ARMA data where it's hard to get absolute abundances. Okay, so the point I want to make is that we predicted that this line would not be as strong as they said in the original paper. And in fact, that is the way that it seems to be going. So they claim that, well, the fact that it's only 1 part per billion there could be reconcilable with the 20 parts per billion from JCMT if there's an order of magnitude temporal variation in phosphine. So they could claim that, maybe there was just a really big discrepancy in phosphine. And I just want to point out, in this recalibrated data, the HDO line is solid. That is a solid detection. They did, in fact, detect HDO. So they are able to detect molecules in this data. It's just that the significance of what's at the phosphine position is going down. So Alex, in the process of working with us on our paper, was also reanalyzing the ARMA data, the recalibrated ARMA data, reanalyzing that as well at the same time. And what he discovered was enough that we actually split that off as a companion paper, because he said, I need more room to, we were going abstract letters. He said, I need more room to explain what's going on here. So he actually did that reanalysis. But when he did the reanalysis, he didn't get a 4.3 sigma detection. This is his reanalysis of the data. He sees nothing of any particular significance, at that position. So this is the recalibrated, reanalyzed data, and independently reduced by Alex, and he was not able to verify that 4.3 sigma detection of phosphine at that position. So the fact that there seems to be nothing at that position, or if there is something there, if we believe the Greaves et al. Analysis, then it's very weak. Then that supports the SO2 hypothesis, which would predict that the line is not there or highly suppressed. Okay. So other bits of evidence. Whenever you're trying to say that you have a particular molecule in an atmosphere, the gold standard is observing it at 2 different wavelengths, right? To be able to say, okay, I've got this line. I make the analogy of a barcode. If you pick a barcode up for like 6 different items in the grocery store, you might end up with a particular line at a particular position in like 5 of them, but they're all very different products. It's not till you go elsewhere on the position on the barcode that you'll see this sort of discrepancy in the lines that helps you discriminate what this thing actually is. So we have something with a barcode where both phosphine and SO2 are at that position. Now we need to go off and find something else in the barcode range that actually tells us that we're looking at SO2 or phosphine. So they went looking for phosphine this is the TEPS instrument again. So this was existing data from 2015 that was pulled out of the, out of the mission to the back of my desk drawer, basically pulled out of archive, and the original observers reanalyzed it, looking for phosphine lines at 10 microns. And here's where the phosphine line would be at about, say, 20 parts per billion, if that's really what was going on there. And this is in fact the data, and they see it's on the edge of a telluric water vapor line, but you see no sort of bump in the water line that indicates that in fact the phosphine is there. So no phosphine was detected, which failed to confirm, phosphine with a second spectral feature. And they set an upper limit of no more than 5 parts per billion, which was 4 times less than the original claim from Greaves et al., but still potentially consistent with their 1 part per billion. Okay, other people dragged out previous spacecraft data. So this is the VEX mission again, Venus Express, looking at observations near 4.1 microns this time instead of 10. Sorry, I don't know why this keeps advancing. 4.1 instead of 10. And so again, looking for a feature that would have looked, like this. The blue thing here is the phosphine absorption as it would be at 20 parts per billion. This is the data that was returned by the mission. And so they, again, did not see phosphine there, and they're actually able to derive in some instances in their data upper limits of 0.2 parts per billion in their data. That was sufficiently high precision. Although they had looser upper limits in some of the other data where it wasn't as precise, of 6 to 8 parts per billion. And so we don't have the validation there. Greaves et al., when challenged with this, basically said that the Venus Express and infrared observations in Hawaii did not peer as deeply into the Venus atmosphere, and therefore we should not be surprised that they did not detect phosphine. And that was a quote from this week. So this group is still, even though they've been presented with the data that whatever's absorbing seems to be above the clouds, are still arguing that whatever is above the clouds and these validations are not able to peer as deeply as they think they were able to see with their data. And then therefore that's why we're not seeing phosphine being validated. So phosphine, as we said, doesn't make a lot of chemical sense in the upper atmosphere because it's destroyed really, really rapidly. But here's a typical SO2 profile in the mesosphere above the clouds, and it in fact increases with altitude because it's generated in the mesosphere from a bunch of different reactions, including photolytic ones. And so, it makes a lot of chemical sense for this absorption to be SO2, which is as happy as a clam up in the mesosphere. It doesn't have a problem at all, whereas whereas phosphine is just destroyed really rapidly. Okay, so when the Villanueva paper went out, the Greaves et al. In the debate, they pushed back and said that actually you couldn't fit their absorption line. By the way, here's a slightly less pretty version of the JCMT data at higher resolution, so you can see what they're claiming to be this 4.3 sigma detection. Sorry, this keeps advancing. No idea why. And so here's their preferred line, and they're arguing that this fit here with 150 parts per billion of SO2 isn't the right width. But we did a full-up radiated transfer model, and we can absolutely get it to be the right width. And just to show that we're not, again, we're being very careful, Andrew went off and also tried to fit existing ARMA data at a different wavelength. This was, actually I should have referenced this, but this was an Oncarnaz et al. Paper using ARMA actually in its cycle 0. So one of the first ever observations used with ARMA for Venus. But we were able to absolutely nail both the abundance that Therese retrieved, we put that in, and then we were able to fit both the width and whatever. So I think our radiated transfer is good, and we were able to fit the JCMT line with that width for that abundance. And then the other argument they came back on was saying that given that the data shown are compatible with the presence of the model's line wings, there's no empirical evidence that phosphine lies only above 70 kilometers. So what they're saying here is that we're saying, hey, the phosphine's way up in the atmosphere, not in the clouds. And their argument is, oh, but it still could be in the clouds because the stuff that's in the clouds would contribute to the line wings. And the noise is such that we cannot see or quantify the line wings. all right? So the point with that, though, means that there's actually no evidence that phosphine exists below 70 kilometers. That they're arguing in defense of what we're saying, which is that the data are insensitive to the cloud region. We cannot see anything that would indicate that phosphine is actually in the clouds, but we do have pretty good evidence that something is absorbing above the clouds. And that's the thing that has to be explained. And then just to throw a grenade into all of this as I wrap up here, the JCMT data detection may also not be significant. So people have also started looking at that data as well. And so this is a paper, so it's only a single person at the moment. So this is a paper by Thompson. He used 2 line detection methods to assess the statistical reliability of the JCMT detection. And he used a higher order polynomial to fit and a lower order one, and he used a bootstrapping technique to figure out, based on the result that they got, where in the universe of possible results with that data analysis technique, shifting by wavelengths and doing perturbing the way it was fit, is it actually significant? And he basically found that the polynomial fitting results again could have produced a false positive detection in the JCMT data. And concluded based on his bootstrapping that there was no significant evidence for phosphine or SO2 absorption in the JCMT Venus spectrum. And as you can see, as I pointed out here, this is the JCMT detection. And you can just see in the continuum, the noise level on either side, that it would not be hard to believe that that's not actually significant. So does that depress me? No, because again, remember that the 1 sigma change in the JCMT significance dropped our assumed phosphine by like a factor of 2, which is still well within the factor of 10 range that's been seen in the SO2. So even if there was no detection in this JCMT data, it would not rule out the SO2 hypothesis. That would just say there's less SO2 there than we thought there was, but certainly not not outside the realm of a temporal variability in SO2. So wrapping up, so this was a New York Times article that came out on Monday. Life on Venus, the picture gets cloudier. And this article was actually inspired by our 2 papers coming out, although it's more of a big overall look at, whether or not the 2 sides of the argument. So it's worth a read. That's pretty good. So despite claiming evidence of phosphine in the Venus clouds from what appear to be 3 detections of a high signal to noise feature at 266.94 gigahertz with apparently no contamination from SO2, that was the original paper, I think from our papers we conclude that there is no evidence, and this is building from multiple papers and in fact from their own admission, that there is no evidence of phosphine in the clouds, okay? But there's evidence that something absorbs above the clouds. That doesn't mean that phosphine isn't in the clouds, but anything could be in the clouds. They simply have no sensitivity to it, right? But what we do have from their data is something is absorbing above the clouds. That detected absorption is coming from the mesosphere. If it's phosphine, it's not consistent with in-cloud generation because that would have been destroyed. Phosphine at those altitudes requires an unrealistic flux, 100 times Earth's O2 to persist there. But SO2 absorbed at the same frequency is common and is known to increase with altitude above the clouds. So our other conclusion was that SO2 can explain the data without phosphine. It's therefore less likely that it's due to phosphine. It doesn't rule it out. It's very hard to rule it out. It could be there at a 0.2 part per billion level, but the data is just not good enough to tell us that it's there. The reason we think this all fits is that the SO2 absorption would have been heavily suppressed. So the non-detection of SO2 is still consistent with the normal abundance of SO2 in the atmosphere. And when you use that normal abundance on the JCMT data, which was single dish and should have seen everything, then you can fit it without the need for phosphine. And then of course we predict that the 266.94 gigahertz line would not have been there at any significance. And as time has gone on with the recalibration of the data and everybody else looking at it, that is in fact what has happened. So our prediction is now coming true, that in fact that feature will be less significant in the data. And then of course there's just the fact that observations at other wavelengths did not detect or corroborate phosphine at the amount that was claimed in the original discussion. So where do we go from here? Well, we need some future observations, I think. As I said to a reporter, there's still kind of enough wiggle room in here. I mean, they could hide a tiny amount of phosphine in these fits. We can't rule that out. And the fact that the SO2 was suppressed and doesn't provide a positive abundance determination is problematic in trying to figure out, what fraction of that line is due to SO2. So I think we need some follow-up observations, preferably single dish, so they don't suffer from line dilution and we don't have to worry about any of that stuff. And these again are recommendations from Alex, who's the expert. He says, well, if we use the Atacama compact array, which included the shorter baselines, which made it more sensitive to the whole disk distribution, rather than the primary ALMA array, that might be a better way of observing. And also, you really want to get near simultaneous, like within a few hours, observations of the SO2 reference lines in addition to the 266.94 blended phosphine plus SO2 line. And Alex has already figured out sort of the configuration that you would need for ALMA to do that. So the observation should occur when Venus has a small apparent angular diameter and is less resolved in the ALMA antennas. That will also help with the ripple effect that was going on. So this really needs to be done very thoughtfully and very carefully by people who are Venus experts to go and get the right data. So this is my, I believe, okay, nearly final slide. So what do we take away from this? This was actually, from an astrobiology perspective, a really interesting test run on future exoplanet biosignature assessment, right? And again, it just relays a point. I believe this is one of my main themes, one of the VPL's main themes, that understanding the environment is absolutely key to searching for life. It's important to characterize the environment and have colleagues who understand that data and who understand that environment. And of course, with exoplanets, we're all going to have to be understanding the environment right from the start, but we'll need to prioritize in doing that. So the increasing confidence in a biosignature discovery requires 4 critical checks, and we're seeing this play out in the Venus thing. You need a confirmation of the detection. Did you actually see anything? If you did see something, you need a confirmation of the identification. Is the thing you saw the thing you think it is? Okay. If you get past those initial tests, and it's not clear to me that Venus is getting past those initial tests for the phosphine, then you need to assess the likelihood of abiotic formation mechanisms. Is it possible, if this is truly phosphine, is it possible that it's produced by some abiotic planetary process? And if you get past that hurdle, then there's another hurdle which says, what is the plausibility that life actually generated that product in the environment? Because you can come at this source argument from 2 sides. One is it possible to do abiotically, or how likely is it that life could actually do this process? Because even if you can't think of the right abiotic formation mechanism, you could potentially rule it out just on the gross improbability that life processes could get through that process. So the bottom line is, if we don't understand the environment and potentially its history, we can't accurately assess the likelihood that something is a biosignature. Unless it's a modulated radio signal that encodes pi, in which case I don't need any environmental context whatsoever, because that is such a statistically complex and unlikely event that I don't need to see it in context. So my final slide, what do we take away? All right, test run for future biosignature assessment. We have to ask us question, is this the way we want it to go? Do we want it to be a fight in nature communications? Is there a more collaborative community-wide process that could lead to a better outcome for this? And if so, what is the best way to incentivize this? Because that would really change the way that we do science. But I think it might be something that we actually need to do as an astrobiology community. And stay tuned, because I and Heather Graham are leading a new NASA workshop, which will happen sometime in May, which is a joint Enfold and Nexus activity looking at standards of evidence for biosignature detection and also protocols for reporting biosignature detection. So that's where we are. So I will finish up there, and hopefully there's still some time for questions.
Thanks, Vicky. That was awesome. You made my week. And I really hope that I'm never on the wrong side of a scientific debate with you. It just seems like you kind of ruthlessly dismantled the case for phosphine. All right, are there questions from the audience? You can raise your hands, which, in case you haven't been on Zoom in a while, is down in the reactions button, like the same place where you laugh and give thumbs up. So you can raise your hand. Or otherwise, if you can't find it because you're a Luddite, you can just unmute yourself. I guess as like a warm up, so I was wondering, as you were talking about this, I was wondering about exactly the lessons to be learned for astrobiology, for like exoplanet astrobiology. And one of the things that you did not harp on, but which I was a little bit concerned by, is, at least my understanding from the outside, is as a result of these splashy papers, there was like actual money got given to people to start doing more Venus research. And so on the one hand, I'm like, that is really horrible, because that's like a really terrible incentive for people to have to sort of, I don't know, cry wolf or something. But then the flip side is like, oh, maybe something good came out of this after all. You know, much like when people claimed Planet 9, it led to a whole bunch of new discoveries of objects out there that are not Planet 9, but that may be interesting nonetheless. So I don't know, like, how do you feel about this with the benefit of some hindsight? Like, do you think it was all a bad thing, or did anything good come of it, or what lessons would you take out of it?
Yeah, I think I am concerned about the downside might be that once again we're kind of putting the public through an emotional roller coaster. I do worry about that, and that we're setting up this. You know, some people might say, well, maybe the Mars community has done this already, but you know, I do want to have some process where that sort of thing doesn't happen. So I see this as being, as I said, it's a test case. So even if it is negative, at least it's a test case that really heightened our awareness of what we need to do. And we had been thinking about running this biosignature standards of evidence workshop for quite some time, but believe me, we are really focused on that now, right? So that certainly came out of it. It really kind of gave us a jolt. I don't think we as a community thought we were that close to an actual life detection claim. And so at least not, you know, in kind of the remote sensing sense, you know, potentially on Mars, looking for the methane and so on and trying to interpret that. So I think it really has inspired us to really focus on something sooner rather than later that we really needed to do. I think it would be a good thing if, I mean, the bottom line is, you know, Venus is as a Venus scientist, I'm also kind of cranky because Venus is actually a really interesting planet. It has so much to teach us. It is, you know, as I said, it is the planet most and least like the Earth. How did that happen? You know, it forms in the same place, potentially with the same volatile abundance, although maybe that's not the case. But, you know, it has this very different evolutionary path. It is a prototype for hot Earths that we will detect and characterize first with missions like JWST. You know, there's so much, and it's 0.3 AU away at closest approach, and we know very little about it. And I think that, you know, leaves us vulnerable because honestly, we don't understand the chemistry within the clouds very much at all. And so I would argue that Venus is astrobiologically interesting because there is no life there, right? That it kind of serves as both sort of an evolutionary outcome experiment and then also, you know, testing our understanding of environments and, you know, the limits of habitability, essentially. And so I think we should have missions to Venus anyway. And I'm concerned that when you push something as flashy as this forward and then it gets pulled back, people are like, oh no, well, maybe we shouldn't go to Venus. It's like, no, we should. So yeah, I'm worried about sort of this roller coaster of interest. And I think there's also ramifications that you might not think of. If people claim that there's life there, it puts planetary protection constraints on missions. It increases the expense of them. It complicates things a great deal. So I think you want to be very careful about making claims like that when you do planetary exploration, right? So I'm not sure the discoverers of this thought through any of that, but it really does change the ramifications for missions that go to Venus. And I, you know, I'm a Venus fan. Venus was my first love as an astronomer, and you know, I really think we need to go to Venus. It's a fascinating place. But yeah, I just worry that things like this maybe put the emphasis in the wrong place, and then pull that emphasis away, which could be a net bad thing.
Right, René, you've had your hand raised.
Yeah, a quick comment. So first of all, yeah, thanks. This is a great talk, and I agree with Nick. You've made the case. So I did not follow the literature in details, but when you look at the data, I mean, first of all, I think it really emphasized the need for, you know, how important data analysis is, and and also the difference between the various communities. You know, in our world of exoplanet and time series, and when we see the data set like this, oh, well, let's do a Gaussian process on this to assess whether that line is actually significant. So I'm curious to know whether there's been any this kind of analysis using Bayesian framework to assess the significance of that little line, whether it is phosphine or even SO2. Yeah,
I'm not, I mean, maybe look at the Thomson paper. I'm not sure what was in the bootstrap algorithm he did for that. And I have to admit, I only looked at that paper relatively recently. But yeah, I think you're right. I think there needs to be, you know, a concerted effort by multiple groups using multiple techniques to go into this. But I mean, there's the Snellen and al. Paper. I'm not exactly sure what Ignace used. But yeah, people have certainly tried to reanalyze the data. I don't know if they're specifically using the technique you're describing there. But
and Thanks. One final comment. There's this graduate student here, Karine Piolet, was in the field this discovery. We got actually data with Spiru on Venus, and so there's SO2 and phosphine lines in K band. So maybe these lines are there. So we just dig them out. It's a challenge to reduce this data. But
yeah. Oh yeah. No, I mean, again, Venus observing is really hard, and that's the other thing. You know, if I want to be mildly critical of the team, is that they didn't really have Venus. They had one Venus expert in there, but he was, from what I've heard, he was kept at arm's length, and so you know he wasn't as integrated into the team as it could be. So I think the other message from here is, you know, if you can get the experts in the environment, you really should, you know, bring them in on this, because it's so important to understand. Yeah, again, it's not just the detection. It's not enough to detect a biosignature. You have to interpret it correctly. And I think that whole holistic ecosystem of trying to interpret it correctly, including, the detection significance is part of it, which is what you're pointing out, Renee. But also, I would argue that, you know, you really need to have people who know what to look for and know when things are odd. I mean, the chink in the armor for me was just 10 parts per billion of SO2 in the clouds. What the heck? You know, and if I hadn't seen that, you know, I might have. I mean, it looks very convincing to me when I first read it, you know, seeing all of that data up there. But there was just that tiny chink, and that's because I knew something about the environment, and that caused me to go in there. And we're not going to have that with exoplanets. You know, we're not going to have the ground truth, and we're not going to have this body of previous characterization. So in that sense, it's not a true analogy, but it does point to the importance of, you know, not just looking for, I mean, when I grew up in the TPF world, you know, people were saying, let's do matched filter bands on O2. We'll do one on the band and one on the continuum, and we are done. You know, and I think I always had antibodies to that approach, but it's really stronger now. It's like, no, you can't do that. When you go in to look for biosignatures, you really have to get as broad an understanding as you possibly can, because otherwise you'll just interpret things wrong. So, you know, that's what will happen.
thank you.
All right, other questions for Vicky? Well, if not, I hope you will advertise this workshop that you're organizing very widely, because I know that I've wondered about this. This has come up at previous ExoClimbs meetings, that, you know, it seems inevitable that in the James Webb era, someone is going to get, like, you know, New York Times above the fold front page, hey, we detect ozone on some planet, therefore there's life, or whatever it is. And then it'll be exactly these questions like, did you actually detect a line? Could that line be something other than ozone? And et cetera, and like working the way down the list. And so I think it'll be really important to have some sort of protocol, and to make sure that it gets advertised widely to reporters so that they know what the protocols are, and that they can get a feel that, like, oh, these scientists they're cutting corners, like they're not actually doing things properly.
Right. I mean, that's the hope. And we can't force anybody to do anything, and we don't want to censor anybody in their science, obviously. But what we would like to set up is some set of guidelines where it's clear that there's an advantage to the community in following the guidelines, and where, external agencies like journals and the media, for example, can, you know, editors can potentially come in and say, well, you know, or reviewers could come in and say, well, you didn't follow the protocol. Could you possibly do that? So, I mean, just by setting up that structure, we hope that the system can, you know, potentially have something to use to reinforce these sorts of more rigorous looks at things. But yeah, we are totally planning on bringing in the media and also journal editors.
Good idea. Great.
Yeah.
Okay, well, if there are no further questions, let's thank Vicky again, using our little clappy things. Yeah, again, that was magistral. It was amazing. You kind of walked through everything so thoroughly. I feel like
a long time though.
Yeah, I feel like I actually understand it now.
Yeah, when I was talking to reporters, they were like, "Yeah, but how do you know it's above the clouds?" And I'm like, "Well, you know," and it's hard to explain. But thank you for sticking with me through all that. So.
Victoria, I would have a very short question or comment. What do you think about the whole coming back at the Oumuamua story in the news lately?
Yeah, I mean, that's sort of another analogy where, you know, basically people are proposing unnecessarily complex explanations for something that could be simplistic and natural. And I think, you know, we have to, you know, as scientists, we have to recognize that that's not a great way to go, that you know, that you need to, and they are kind of, they're kind of in the similar spectrum, although I would argue that the Phosphine on Venus, I think that was, you know, there may have been some confirmation bias there, but, you know, at the very least, they were trying to do a science experiment. They tried to verify it. They went through the steps. They did everything that was scientifically, I think, right to do. It's just the interpretation was not quite there. But in the Oumuamua case, I will say that, you know, claims like this do tend to, I don't like them because they put the proof back on the community to prove that it's something ordinary. And I don't want to be in a community where that's the kind of thing where you get to say something and then the community has to, I mean, I dropped everything and that's all the science I did for the last 4 months. And that wasn't in my plan. So, you know, I think it's also important for us as a community to recognize the burden that gets put on the community, you know, when this sort of thing happens. So I'm obliquely saying, I think that's a negative thing to come out with claims like that, where, you know, people have to stop and explain the actual rational explanation. So I'd rather people didn't do that.
Vicky, I just saw a question in the chat from Lisa. Do you want to go ahead, Lisa?
Oh, okay. Yeah. So I have just a short comment on what Vicky just said. You should have a look at the new Forbes article. There's actually somebody who's taking this whole claim to town because he was just talking exactly about how scientists should not do this. He's just posted it yesterday or the day before. So that's an interesting one. I could send it around.
Yeah, the Ethan Siegel one. Yeah.
Yeah, the Ethan Siegel one. Thank you.
No, we're inviting him to the workshop.
Perfect. Good choice. But my question to you is, and you touched on this, but how can we actually get a little bit of a better understanding of the clouds, you know, whether they have phosphine or not on Venus? Is there any lab work that's done currently or that we could do? Or because clouds on the Earth are so tricky, you know, making them out of different things, it's got to be made worse to just understand what we see.
Right. Well, I think you know, the gross composition of the clouds is known. I think it's, again, really important to go into the clouds. There were the Vega balloons that were in the clouds and took measurements at the time, but we haven't gone back and really sampled the clouds as a target. There've been Venus Express has been a remote observing, you know, orbital capabilities, but I think it's time to get back in the atmosphere and in the clouds to make those measurements, because it's, I think, you know, Venus laboratories are very difficult to create just because of the physical extremes of the environment. Although, you know, within the clouds, it's more of an Earth-like environment, you know, as far as pressure and temperature are concerned. But yeah, I think this is really a solid case for why we need to go back to Venus and study it in situ.
Okay, well, thanks again, Vicky. It was lovely to see you again, and thanks for the science update. And we'll have to have you again another time to hear the exoplanet science update. But you know,
sure,
we can wait till there's actually some James Webb data, and then we can get into a real debate.
That would be awesome. Let's hope we get some actual data. Photons are coming, as we like to say.
All right, take care. Thanks, everyone.
All right.